As we've hinted at a few times already, every end device in a SAN, host HBA ports and storage array ports have worldwide names and endport IDs. Worldwide names are manufacturer assigned and burned into HBA cards, whereas endport IDs, which we actually sometimes refer to as FC IDs or fiber channel IDs, are dynamically assigned to devices when they log into the fabric. The point being though, every endpoint in the SAN has both a worldwide name and an endport ID. And back in the day, it was a simple one-to-one relationship like this: one HBA port with one worldwide name and one endport ID. And that worked fine. That is, until we started virtualizing servers. Then we suddenly had multiple virtual servers running on a single physical server. And that single physical server had maybe two HBA ports, so two worldwide names and two endport IDs. But what if you wanted 6 of your virtual servers running on a single physical server to each have their own worldwide names and endport IDs? Well, we couldn't do that, and that's where Npiv, Endport ID Virtualization, came into play. Npiv allows a physical HBA port to register itself for multiple endport IDs when it logs into the fabric. Now, in order to do that, the HBA port has to have more than one worldwide name assigned to it. We can see in our updated diagram that our physical single port HBA card has registered for 2 endport IDs with the fabric. This could easily be 3 or 4 or even more. Now in our diagram we can see that our physical HBA card with a single physical port has registered 4 worldwide names with the fabric and received 4 endport IDs. Your operating system and hypervisor can now do whatever they want with these additional addresses. Now, let's talk about Npiv. Npiv is an acronym for Endport Virtualizer, and it is based on Npiv technology. But whereas Npiv is a technology used by end devices such as host HBAs, Npiv is a technology used by switches. The main uses for Npiv are to allow switches from different vendors to exist in the same fabric without having to operate switches in interop mode. And also, they allow the number of switches in a fabric to scale better. Normally, when a switch joins a fabric, it participates in all fabric-related services and functions. It holds a copy of the name server database, zoning database, everything. The problem being, switches from different vendors participating in the same fabric never really worked, and you had to put your switches into clunky interoperability modes that were a nightmare to work with. Also, as you start to scale fabrics with lots and lots of switches, you started to hit scalability issues. In particular, the number of domain IDs supported in a fabric can be a limitation. Basically, each switch that joins a fabric requires its own unique domain ID. And a domain ID is just a unique identifier for a switch within a fabric. And the dynamically assigned endport ID that every endpoint on our SAN has includes the domain ID of the switch that it's connected to. Anyway, Npiv helps with both of these issues: interoperability with switches from different vendors and scaling the number of switches in our fabric. What happens is, when an Npiv switch registers with the fabric, it pretends to be an end device instead of a switch. Specifically, it pretends to be an endport running Npiv. As a result, the Npiv switch isn't assigned a domain ID, and it's not expected to participate in fabric services. After all, it's pretending to be a host, not a switch. This obviously then means that the links between the Npiv switch and the non-Npiv switch isn't an interswitch link, and the ports on either end of the link don't configure themselves as e-ports. It's literally just as if a host HBA had logged into a switch, so it's an N-port to an F-port connection. Simple as that, but very powerful in scaling fabrics and enabling heterogeneous fabrics, fabrics with switches from multiple vendors. Right, let's talk now about multipathing. Mpio is the common acronym for Multipath I/O. At its core, Mpio is about both redundancy and performance. Let's take a look at some images. In our diagram on the slide, we've got a single host with 2 HBAs. One HBA is connected to red switch and the other to green switch. And importantly, on our host we have Mpio software. Now this could be specialized software purchased from your storage vendor, or it could be the default Mpio software that ships with most operating systems such as Windows and Linux. We see that each of our switches is connected to a different controller in our storage array, so it should be real simple to see how this configuration is resilient to component failure. The components highlighted in red represent one path to our storage, and the components highlighted in green represent an entirely separate and independent path to the same storage. We could lose a single HBA in our host, a single switch, a single cable, or a single controller in the storage array, and still be able to access our storage over the alternate path. Now then, these multiple paths can operate either as failover only in an active-passive mode, or as true active-active using algorithms such as round robin. Let's take a look first at active-passive or failover only. In this modus operandi, all I/O from the host to the storage occur over only one of the two paths. In our diagram, this is the green path. The red path is passive, and it'll only be used if the green path fails. However, if our host has two volumes from the same storage array, the green path could be active for one volume and the red path active for the other volume, giving us a more active-active type model of operation, but still only a single path is active for a particular volume. Now, active-active, sometimes called round robin, is where both paths, green and red, are active at the same time for a single volume. This allows the I/O to be evenly balanced across both paths. This mode of operation obviously requires a storage array with true active-active controllers, where multiple controllers can own and write to a single volume concurrently. And finally, it's possible to have more than two paths to a volume. Now looking at our diagram, despite the fact that we only have two HBAs in our host, we actually have 6 paths to our volume, 3 via the green fabric and 3 via the red fabric. Now from a redundancy perspective, we don't have 6 totally independent paths, as 3 paths rely on the green HBA and cable from the host to the switch, and the other 3 paths rely on the single red HBA and the red cable from HBA to switch. However, what we do get is the processing power of 6 array ports, and also losing any of the 6 array ports will only reduce our connectivity by 1/6 rather than by 1/2 if we only had connectivity to 2 array ports.